Next talk in this session, provable security for onion routing and mixed network packet format Sphinx.
Thank you for the introduction. I'm Philip Scher from KIT, and I have the pleasure today to present to you our work on provable security for the onion routing and mixed network packet format Sphinx, joint effort with Christian Weiss and Thorsten Struve. So, Sphinx. When we're doing onion routing, mixing, we need an underlying packet format that can actually carry our data through the network. Sphinx is one of those formats by Danetsis et al., and it's compact and provably secure, which makes it interesting. As a quick refresher on onion routing and also an introduction to our notation, we're interested in obscuring sender-receiver and sender-message relationships, and the way we accomplish that is that when we have multiple users like Alice and Carol trying to send messages to Bob and Dave, they send their message through multiple relays, and if they share an honest relay, in our notation, adversarial relays are marked in red, honest relays are black. If they share an honest relay, then the attacker won't be able to link what comes out of that honest relay to what went in. And so that's how we hide our links. Now there are two different ways to construct these networks. We call them the integrated system model and the service model. In the integrated system model, the receiver is itself part of the network. So in this case, Bob is itself a relay in the network. While in the service model, receivers are external to the network. So there might just be like normal web servers, and instead the final relay in the network is responsible for communicating with them. This may seem like a minor difference, but it will turn out to be very crucial right now, because unfortunately Sphinx is susceptible to a malleability attack. In Sphinx packets, only the path information in the packet that says which relays we're routing through is actually protected by a MAC at every hop, while the payload's integrity is only verified at the very last relay. This is due to technical reasons with the packet format's construction. What it means is that the adversary can flip bits in the payload of the packet to effectively tag it. This completely destroys the payload, but at a later point in the path, like for example here, if the adversary tags Carol's packet, and then we have Dave, who is an adversarial receiver, receives the packet, sees that the payload fails the integrity check, and now knows that Carol was trying to message him. So now we have a global adversary that can link senders and receivers, which is exactly what we were trying to prevent. This problem affects several protocols that use the Sphinx format, including Hornet and Taronet. However, Sphinx wasn't actually originally designed for the integrated system model. It's actually a service model format. And when we try to perform the same attack in the service model, we see that the integrity check will now fail at the final relay, not the receiver. And since the payload is destroyed, which also contained the receiver's address, now the attacker doesn't actually learn anything useful. They only learn the link between the sender and the final relay. Under the assumption that the final relay is chosen randomly, for example, that's useless. So, what are we trying to do? We could mitigate the tagging attack. There are approaches to do that, but they either have massive costs in efficiency or impact the packet format's functionality. So instead, what we're going to try to do is prove that Sphinx is secure in the service model. There are a couple steps to doing that. First, we need to actually provide a formal definition of onion routing and mixing in the service model. Then we need an analytical framework to actually compare Sphinx against. We need to make an adjustment for Sphinx to actually be secure in this framework. And then we need to do the proof. And the result will be that we'll have provable security for a highly efficient OR and mixing packet format. So about the whole adjusting Sphinx part. Sphinx supports replies, so receivers can send replies back to the senders. This is done via anonymous return envelopes that the sender prepares beforehand. In the original construction, Sphinx uses a NIM server to implement these replies. So the senders actually send 2 packets, One is the regular packet that goes through the normal path to the receiver, and the second one goes to the NIM server and contains the return envelope. The NIM server will then store the envelope, and when the receiver wants to reply, it sends its reply message to the final relay, which forwards it to the NIM server. The NIM server will assemble the packet from the return envelope and the message and send that back through the network. This is susceptible to a tagging attack, the same one we were talking about earlier. If we have an attacker that tags the packet containing the return envelope as it leaves the sender, then the NIM server will receive a destroyed payload, and so it won't be able to store the return envelope, which means that later when the final relay forwards the message, there won't be anything to pair it up with, and an attacker-controlled NIM server or an attacker that can observe most of the traffic of the NIM server will then be able to link the sender to the final relay and thus the receiver. We get around this by removing the NIM server from the network. Instead, we take the return envelope and put it in the payload and just send it to the final relay. This eliminates the separate packets we were sending to the NIM server at the cost of increasing our payload sizes. So now we've adjusted Sphinx. We need an analytical framework so we can actually, prove anything. The existing frameworks for onion routing and mixing don't account for the malleability with tagging or for service model networks. So we need to make a new framework. For that, we adapt Kunit-A's framework for the integrated system model into the service model. This comes with 3 game-based onion properties and 1 ideal functionality. And in combination, the properties, which are comparatively easier to prove, are sufficient to realize the ideal functionality, which would be more difficult to prove directly. And now, all that's left is the easy part. Full security proof. Sphinx did originally come with a security proof, however that one was based on incomplete properties that weren't sufficient to actually prove security. So we make a new detailed proof based on our onion properties in the new framework. In doing so, we make another discovery. The original underlying assumption for Sphinx's security was the decisional Diffie-Hellman assumption. We also discover that that's insufficient, so we switch to the gap Diffie-Hellman assumption, which states that the computational Diffie-Hellman problem is hard even when you're given a magical DDH oracle that solves the DDH problem for you. The good thing is, the gap Diffie-Hellman assumption is generally assumed to hold in standard elliptic curve groups, which were already being used with Sphinx. So this doesn't actually, you don't have to change the implementations. You're just using a new assumption. And with that, we have the first full detailed security proof of Sphinx. There are some things you need to be careful about when using Sphinx to do it securely. First of all, yes, you have to embed the return envelopes in the payloads, as mentioned earlier, because using the NIM server would allow for the tagging attack. The NIM network, which also uses Sphinx, already does this. Their return envelopes are embedded in the packets. And secondly, as mentioned before, the tagging attack does still allow you to link the sender to the final relay. So that link must not reveal critical information. So your choice of final relay can't depend on the sender or the receiver or the message, but you can choose final relays randomly or based on load balancing, for example. So, and with that, we re-established Sphinx as a provably secure base for onion routing and mixed networks. In summary, we provide the first formal definition of service model onion routing and mixing, an analytical framework for onion routing and mixing packet formats in the service model, an adapted version of Sphinx that works in this model, where we embed return envelopes and payloads instead of sending them via the NIM server. Then we provide the first full detailed security proof for Sphinx in this model based on the gap Diffie-Hellman assumption, and we provide criteria for secure usage of Sphinx. And if you're still interested, then check out our paper. Thanks for listening. Mike is moving towards you.
Thanks, Hawk. I like these results. You mentioned that there's an attack on Sphinx packet format based on the reply going through the NIM server. Was there a fault in their proof, or did their security properties not address the scenario?
The security properties were incomplete in multiple like for one, they're not sufficient for like the packets themselves, and they also don't account for the existence of an NIM server.
I see. Okay.
So yeah.
Thanks.
So you say NIM already did this. Did they know or suspect, or did they, for logistical reasons, not use a NIM server and they got lucky, or?
I haven't asked them. I suspect they did it for like logistical reasons, because the NIM server is also like a central point of failure in the network and a pretty juicy target for an adversary. Like, it's a server that every reply message goes through.
Harry from NIM. I mean, I think that the issue with NIM servers is that it's a really old design that's kind of email based, and Lupix et al. Like they don't use NIM servers. They just use normal servers. You can drop off at gateways or mixed nodes or whatever. So I did actually. I also noticed it was a bit odd, not because just like common practice. Like, why would you not integrity check the payload? Did like George just forget, you know? And it is a, like George Denises is not an idiot. I did ask him this question, and he basically had a counter argument, and it's related to the email issue, where he basically said, well, if you do an integrity check and you're under this kind of active attack, then the packet just gets dropped, right? So you don't know you're under attack. Because Sphinx was invented for email, if someone did do a bit flipping attack and the receiver received garbled text because the decryption didn't work, then they would know they were under active attack. So that's just so you know the reasoning for George's original design decisions there. I was wondering though, like, I guess you don't get in this paper, in terms of Sphinx, do you think that this do you really, like, how, in terms of like the proof, how much of the effort was based on doing multiple hops? Because Sphinx was originally for free routing, and it seems like that general design has been thrown out by the community, in which case maybe simpler designs with simpler proofs could be possible.
So yeah, there's a couple things there. The first thing about the whole like integrity of the payload thing, we also looked into, like, there are multiple approaches to addressing the whole thing, and they each have their drawbacks. So like so for example, there is work that like provides integrity on the reply path, but then that starts involving things like zero knowledge arguments, and things get expensive really quickly. And so like also for practical reasons, it's hard to offer integrity on the reply path. For your second question, sorry, I forgot it. Could you repeat it?
Well, Sphinx was built for peer-to-peer
hopping,
and that's
yes.
No one does that anymore. So I was wondering if maybe it could be.
Yes. So the proof, as it stands, works for both models, but yeah, we chose to go with like the very generic approach.
It's good. It's harder. So.
I'm not sure it's actually that much harder necessarily.
Online from Ian.
Hi, thanks. So I'm the MO on the original Sphinx paper. So to address Harry's question about the integrity of the payload, the speaker just referred to it briefly now, but the primary reason that the payload is only end-to-end or sender to exit node, but not recipient, authenticate or MAC'd is exactly because you can't MAC the replies because you don't know what they're going to be, and so only the sender can put the MAC on the replies, which can only be checked at the end. Right, the the nested headers can't include any information about the replies because the nested headers are created in the PI on the slide on the screen right now, and that's before the reply body is known.
Thank you for your input.
But
Let's hear from you.
Okay, let's thank you, speaker.